We'll be starting off with a new chapter, which is diffusion in solids, and the outline of what we'll cover in this chapter includes the phenomena of diffusion. How does diffusion occur in solids? We have two mechanisms that we'll be looking into, the vacancy diffusion and the interstitial diffusion. Both the mechanisms we'll be looking into. Before that, we'll also characterize what is what is self-diffusion and what is substitutional diffusion. So we'll also differentiate between the two terminologies. Then we'll look into Fick's first law. It is basically the law that predicts the rate of diffusion of a species into another species, and this is used for some simple cases. Why do we say it's used for simple cases? Because we assume that the diffusion is taking place under steady state conditions, so which simplifies much of the problem. So this Fick's first law is basically used for steady state conditions, and then within this Fick's law we'll introduce the constant which is known as diffusion constant, and we'll see how diffusion actually depends upon the structure of the material and the temperature. It's basically the diffusion constant that will define. It will depend upon the structure and the temperature, uh, and that would ultimately affect the rate of diffusion of a species into another species. And the second part would be the introduction to Fick's second law. The Fick's second law is basically a mathematical expression, um, which we'll look into, and it is used to solve or address real-time problems, which basically falls under the category of non-steady state diffusion problems. So we'll look at, this is a general solution. Fick's second law is the general solution. It is a general mathematical expression. We'll apply this mathematical expression to one of the non-steady state problem and try to find out a solution for that. This is the scope of this chapter that we'll be looking into. And so let's begin with the understanding of diffusion. Diffusion, as the word says, is mass transport by atomic motion. So species, whether it's atoms or molecules, they are uh, moving from a location to another location, and this is taking place in a considerable amount. Mechanisms in gases and liquids, although we're not interested, but you already are familiar from your high school physics that random Brownian motion basically determines the diffusion process in gases and liquids. However, in solids, the mechanisms are basically vacancy diffusion and interstitial diffusion. These are the two mechanisms in which mass transport takes place in solids, and these two mechanisms will look at them one by one.
सर इन्हें डिफ्यूजन बोलेंगे
किसको?
सर ये वैकेंसी और ये इंटरस्टिशियल
These are the mechanisms. Vacancy
ये भी
diffusion.
डिफ्यूजन में ही आता है
They are the mechanisms by which diffusion takes place in solids, and we'll look into these mechanisms. All
ठीक
right.
है
Now, before we look into the mechanism, let us get ourselves familiar with the term self-diffusion. Self-diffusion, in an elemental solid, atoms also migrate. For example, you have this structure over here shown to you in which you have highlighted atoms A, B, C, and D at time t equals to 0. Let's say after some time, what you would see that A has actually moved to a new position. Similarly, D has moved to a new position, B has moved to a new position, and C has acquired a new position. Although if I would have not labeled these atoms, there would not have been any difference. But just to make you understand that this is a process that is also taking place within the uh, same element itself also. Uh, but it becomes of more importance when you have interdiffusion phenomena. This is the phenomena which is of much importance. And in alloys mean alloy means a combination of two elements or more than two elements. Atoms tend to migrate from regions of high concentration to regions of low concentration. So this is basically the driving force for diffusion. For example, initially, if you have two kinds of atoms in contact, A and B, and this is the interface of the two atoms. If you see over here the concentration profiles at the interface, uh, the A is 100% up till this point, and it suddenly reduces to zero at the interface as you quickly move into it. Clear enough? Then if you look at uh, the atoms B, they are almost 100% as you move in this direction from right to left up to the interface, and as you approach the interface the concentration drops down sharply to zero. Now if you see the concentration gradient for A, it is high over here and low over here, and for B it is high over here and low over here. So A should move from high to low in this direction, and B should move from high to low in this direction. All right. So if you look at the situation after some time, you will see that atoms of A have migrated in this direction, and so does the profile. It changes from 100 over here. Rather than dropping down sharply to zero, it gradually reduces to zero, and at certain distance it is zero. And similar is the case for atoms for B, where it started from 100% concentration and gradually reduces over the distance to 0% as it is shown. So this is basically the phenomena of interdiffusion, where two elements are diffusing into one another by virtue of they having high concentration in certain region and low concentration in another region, and the diffusion takes place from high to low concentration. Is this point clear to you guys?
जी सर.
Yes, sir.
Yes, sir.
Yes, sir.
All right. Now let us look into the diffusion mechanisms as we had mentioned earlier. The first mechanism is the vacancy diffusion. It says that atoms exchange their position with vacancies, and this applies to substitutional impurities uh, present within the material. Obviously, if you look at the phenomena, the diffusion phenomena, you need to have, or the rate of diffusion would be dependent upon the number of vacancies. The larger number of vacancies, the higher would be the diffusion, and it is also dependent upon the activation energy to exchange. What is meant by activation energy to exchange? Let's say you have these two atoms A and B over here, and A has to diffuse into B. The first thing is there should be an empty space present where A could diffuse, and there comes the number of vacancies. If there are number of vacancies present, A would be able to diffuse into it, and the higher the number of vacancies, the easier or the faster would be the diffusion. Number two is that this atom, it has bonds in these three directions. So in order to get rid of these bonds and acquire a new position, there must be some energy that is required to get rid of these bonds and acquire a new position. So these two factors are basically the factors that govern the rate of diffusion in a material. Similarly, as the time is being elapsed, this atom has moved into this new position, and there was a vacancy created over here. So this jump took place, and then with the passage of time, there was a vacancy over here due to the previous jump, and atom jumps into a new position. So this is how the diffusion process continues. That A is moving into B and B is moving into A. But again, the rate depends upon the number of vacancies and the activation energy for the diffusion to take place. Uh, Processing using diffusion, I'll give you an example where you dope silicon with phosphorus to achieve an N-type behavior in semiconductors. If you look at this periodic table, silicon essentially has 4 valence electrons and phosphorus has 5 valence electrons and extra electron. The atomic sizes are almost similar, so they could form substitution solid solution. If you remember the condition, the atomic size should be less than 15%. So what is the process? Essentially, what you do is that you take a silicon slide and deposit at certain locations phosphorus on the surface of silicon. And now, if you see, phosphorus is high in concentration over here, and as you don't go down into the silicon, the concentration is almost zero. So what you do is that you heat this sample so that the two factors are covered. Vacancies are created and activation energy is acquired, activation energy is present, so that phosphorus diffuses from high concentration to low concentration within the silicon. So ultimately, after some time, what you'll have a doped semiconductor region in which phosphorus is essentially doped into silicon to achieve N-type behavior. N-type behavior, how? Each silicon atom is replaced by phosphorus atom having an extra electron that gives the characteristic of an N-type behavior semiconductor. All right. Now, this is again example where you have to restrict diffusion. How do you restrict diffusion? There is a magnified view of computer chip. If you see the lighter region over here, this region is silicon that is used for the semiconductor behavior, and the black region, which in this lower image is shown in lighter color, it is the conductive path. It carries the current from the uh, region in which silicon is being placed from one, I mean, from one component to another. So aluminum is used as a conductive path in this magnified chip. Now, there is another factor which is known as diffusion coefficient. Diffusion coefficient is a factor that defines how slowly or how fastly an atom can diffuse into another, an element can diffuse into another element. So, diffusion coefficient of aluminum in silicon is very small. Or, in other words, aluminum would not diffuse into silicon very easily due to this diffusion coefficient. So you have one thing is that you have used aluminum because it has high electrical conductivity. There are other elements who also have high electrical conductivity such as copper, gold and silver. But the reason of using aluminum over here as an electrically conductive path is because of its very low diffusion coefficient in silicon that makes it difficult for aluminum to diffuse into silicon, making it a stable connection. What is diffusion coefficient? We'll look into it in few minutes time. But you should know the higher the value of diffusion coefficient of an atom in of an element in another atom, it makes the diffusion easier and faster. Diffusion mechanism, which is the interstitial diffusion mechanism, as the word says, there are smaller atoms that can diffuse between atoms. So position of interstitial atom before
सर
diffusion, after diffusion, it is easier for the atom to diffuse within the interstitial position. G.
सर अभी आपने कहा कि हायर द वैल्यू ऑफ द डिफ्यूजन कोएफिशिएंट
G.
ग्रेटर विल बी द डिफ्यूजन पॉसिबिलिटी
G.
सर
Faster would
ये
G.
या
G.
ये सर सर जो दो एलिमेंट्स होंगे जैसे एल्युमिनियम और सिलिकॉन है तो अगर
G.
डिफ्यूजन कोएफिशिएंट उनका ज्यादा होगा तो वो जल्दी डिफ्यूज हो सकते हैं मतलब कि उनकी पॉसिबिलिटीज हैं कि वो हो जाएंगी
G.
तो ये हमें ज्यादा रखना पड़ेगा या कम रखना चाहिए
इस केस में हमें कम रखेंगे ना, क्योंकि व्हाट डू वी वांट? अगर एल्यूमिनियम यहाँ से एल्यूमिनियम यहाँ से सारा सिलिकॉन में डिफ्यूज हो जाएगा तो कंडक्टिव पाथ तो खत्म हो जाएगा.
तो हमें जितनी ज्यादा कम हो सकते हैं उतनी रखनी चाहिए यस सर
जी जी जी, बिल्कुल बिल्कुल बिल्कुल.
ओके सर थैंक यू
So simple enough. Position of interstitial atom before diffusion and position after diffusion. It is basically moving within the interstitial spaces. And as it is apparent, this is more rapid than vacancy diffusion, because in vacancy diffusion you need to have you need to create the vacancies, number one, for which you require energy. Activation energy के लिए भी आपको energy input required होती है, and the atoms are smaller so they can diffuse relatively easier within the interstitial sites. Now, processing using diffusion for interstitial diffusions. An example of interstitial diffusion is case hardened gear. Have you heard the term case hardening?
No
Carburizing,
sir.
nitriding. कभी सुना है?
सर सुना है लेकिन याद इस
सर
टाइम
सुना है, डेफिनेशन नहीं आती, मतलब पता नहीं है कि
All
क्या
right,
है।
right, all right, all right. So what essentially you are doing is, let's say you have this gear. Gear की surface जिस पे wear सबसे ज्यादा होगा, कौन सी surface होगी?
बाय वाली सर।
Obviously, this is the surface that is exposed to the mechanical uh, pressure. The most of the mechanical pressure and wear is basically subjected to this region, the outer surface. So जितनी ये surface hard होगी, the more the surface is harder, the better it would be in terms of its performance at extreme conditions. So what you do is that uh, you expose this gear to an atmosphere which is rich in carbon rich atmosphere. तो बाहर कार्बन ज्यादा है और मटेरियल के अंदर कार्बन कम है. So what would happen is that carbon would diffuse into the surface. All right.
यस
You
सर।
diffuse carbon atoms into the host iron atoms, which is basically the gear is made up of steel or iron. So if this is the outer surface, let's say if this is the outer surface of the gear, you have carbon rich layer over here. This is carbon low or relatively no carbon. So carbon would diffuse into the gear. And this carbon, if I represent it with, let's say, black color, this carbon would acquire space near the surface. And you already know that if you have interstitial atoms present within iron, it would create lattice strain. And that strain is basically a strengthening mechanism. So the surface would become harder as compared to the material which is much below over here within the bulk of the material. All right. तो सरफेस जो है वहां पे चूंकि कार्बन डिफ्यूज हो चुका होगा, इट वुड बिकम हार्डर. और जो बाकी रीजन है उसमें चूंकि कार्बन नहीं होगा, इट वुड बी रिलेटिवली सॉफ्टर. एंड दिस सरफेस वुड essentially become harder. So the presence of carbon atoms make steel surface hard as compared to without carbon. This process is also known as carburizing, and you can also use nitrogen atoms to do that, and that process is known as nitriding. So basically, you are diffusing carbon or nitrogen within the surface region of the material in order to make the surface harder.
सर कोई ऐसा मेटल है जिसके अंदर मतलब है कार्बन ये इंटरस्टिशियल डिफ्यूजन ना कर पाए?
Obviously, जो similar size के होंगे उसमें नहीं करेगा.
नहीं, इतने छोटे हैं मेरे ख्याल से आयरन सर छोटों में ही आता है, छोटे मेटल में आता है।
आयरन से छोटों में आता है क्या मतलब?
मतलब छोटे साइज के मेटल में ही आता है ना आयरन, तो मैं उस हिसाब से बोल
Simple
रहा
is
था
the
फिर
case.
तो
Simple is the case. 15% or less difference in size, you have substitutional. ज्यादा होगा तो you have interstitial. Simple rule आपने पढ़े हुए हैं.
सही से।
Although we cannot predict the motion of one particle when the diffusion is the case, you cannot predict the motion of one particle. However, you can predict the average motion of large number of particles. Point being, particles may move from high concentration to low concentration region. So let's say if you have this image over here, this is your y-axis, this is your z-axis, and this is your x-axis. If you see, the concentration is decreasing in this x direction. So what we say is that suppose the particles are uniformly distributed in the y and z dimensions. That means in y dimension and in z dimension, the distribution is equal. The only variation is in the x direction. So you specify C as concentration, and concentration could be represented as moles per centimeter cube, any quantity per centimeter cube or per unit volume. It could be moles or grams or atoms or atomic percent. This plane would have certain concentration. Another plane would have a different concentration. Another farther plane would have some different concentration as you are moving along the x-axis. So C represents concentration in terms of mole per centimeter cube, grams per centimeter cube, atoms, or atomic percent. And if you see, it's a function of x. So if we look, if you take this plane as C1 and this plane as C2, that means this whole plane is represented by the black line. There is a concentration, higher concentration at this plane 1 and a lower concentration at this plane 2 for a distance which is x1 and x2. And if you see, the concentration is varying linearly. So if the concentration change is linear, that means the change in concentration with regards to change in distance is linear. You can express it as C2 minus C1 over X2 minus X1. In this case, the flux, which is the rate at which particles diffuse across a boundary, this is your boundary. So the rate at which the particles are entering and leaving the system is proportional to the concentration gradient. This is concentration gradient. If you have a linear concentration gradient which is not changing with time and which is basically fixed, the rate is dependent upon the rate which is flux is dependent upon the concentration gradient, or it is proportional to the concentration gradient. This is the fixed first law, which says the rate at which particles diffuse across a boundary is proportional to the concentration gradient, and D is basically the diffusion coefficient, which we had mentioned earlier. It is a constant that defines how quickly one species can diffuse into in another species. The negative term basically is representing that the flux is moving from high concentration to low concentration. That's only the significance of a negative sign. Diffusion coefficient, as it says, is D, and flux is expressed as moles or mass diffusing per unit area per unit time. It could be moles per centimeter square per second or kg per meter square per second, depending upon how the concentration is being specified. All right.
Yes, sir.
सर नेगेटिव साइन क्या प्लीज दोबारा बता दें.
Negative sign just indicates that the diffusion is taking place from high concentration to low concentration, or the flux is from high concentration to low concentration area. All right. Now, if you
सर
look
ऐसा
at
होता है कि
the
diffusion हम लोअर से हायर में करवाएं,
नहीं, ऐसा नहीं होता. In solid,
वो
it's
फिर
from high to low.
फोर्स करना पड़ेगा, है ना?
जी,
वो फिर हमें
फोर्स करने.
फोर्स लगा के, सर
जी जी.
वो फिर लोअर से अगर हमें हायर में करना है तो वो फिर फोर्स लगा के उसको करना पड़ेगा, तो उस डिफ्यूजन को क्या कहेंगे?
नहीं, फोर्स लगा के आप नहीं करेंगे, आप करेंगे यही कि कंसंट्रेशन, लो कंसंट्रेशन रीजन क्रिएट करेंगे तो डिफ्यूजन होगी. I'll give you an example. An example is coming up. Let's see how. जब
Yes.
आपने खुद डिफ्यूजन को डिटेक्ट करवाना है तो what we'll do is that we'll perform an, I'll show how you do that. Let's say you have to purify hydrogen gas from a mixture. How do you do that? So number one, before we move on to the example, we say that steady state diffusion is basically the fixed first law. Concentration at every point does not change with time. That means if I look at this concentration at T equals to 0, it is the same profile. At T equals to 2 hours, the profile concentration gradient remains the same. That means whatever is entering into this region is leaving the region. इस रीजन के अंदर जो है कोई accumulation नहीं हो रही. All right.
Yes, sir.
So purification of hydrogen is a process that you do. What you do is that on one side you have impure hydrogen gas, which contains nitrogen, oxygen, and H2O, and it is separated by a platinum sheet. On the other side, uh, or where you have this mixture, your pressure is constant, so concentration of hydrogen at the inner surface is constant. From outside the surface, what you do is that hydrogen is pumped out. Now you're doing this. How? by keeping a pressure of hydrogen zero at the outside. So concentration of hydrogen on the other side is zero, which you are maintaining. This is what you're doing yourself to create a concentration gradient. Now, inside over here, you have a mixture of nitrogen, oxygen, and hydrogen. Outside over here, you maintain a zero pressure of hydrogen, or hydrogen concentration is essentially zero that you have maintained naturally, artificially. This is the platinum sheet PD having certain thickness, let's say L. So you have maintained a concentration gradient CH and 0. CH at the inner wall at this surface, and at the outer surface, this surface, you have maintained a concentration of 0. This would result in a concentration gradient of 0 minus CH over L, and the hydrogen would selectively diffuse through the wall. That means the flux would be dependent upon the diffusion coefficient of hydrogen within platinum sheet and the concentration gradient, which is CH over L. So now you have forcefully created a gradient. You get the point? Is this
Yes,
clear?
sir. Yes, sir.
Alright.
सर इसको थोड़ा
Alright.
सा यस सर, थोड़ा सा और डिटेल से बता देंगे, ज्यादा समझ नहीं आया।
अच्छा, देखें एक साइड पे आपके पास मिक्सचर है जहाँ पे है हाइड्रोजन, नाइट्रोजन, ऑक्सीजन, एक मिक्सचर मौजूद है यहाँ पे। ये कोई वॉल्यूम है, इसके अंदर ये मिक्सचर मौजूद है जो यहाँ पे प्रोड्यूस हो रहा है, मिक्सचर है। और इस मिक्सचर को आपने प्लैटिनम शीट से सेपरेट किया है। On one side you have this mixture, on the other side of the platinum sheet you have maintained, और आपने यहाँ पे पंप लगाया हुआ है जो कि हाइड्रोजन को रिमूव कर रहा है यहाँ से, such that the concentration over here outside this sheet of hydrogen is essentially zero. Clear?
यस सर।
तो जो इनर सरफेस है, किधर गया ये, फर्स्ट कर रहे हैं, दिस इज द इनर सरफेस। यहाँ पे जो है कंसंट्रेशन ज़्यादा है हाइड्रोजन की, विच इज़ रिप्रेजेंटेड बाय CH, और जो आउटर सरफेस है यहाँ पे जो है हाइड्रोजन की कंसंट्रेशन जो है वो ज़ीरो है। तो देयर इज अ ग्रेडियंट दैट इज you have created. As a result of this gradient, hydrogen would diffuse from the inner surface to the outer surface. All right?
यस सर।
And you would be essentially collecting, यहाँ पे आपने कोई सिलेंडर रखा हुआ है जिसमें ये हाइड्रोजन, प्योर हाइड्रोजन जो है वो आप जमा करते जा रहे हैं। So you are basically getting purified hydrogen through this platinum sheet due to the diffusion. Clear?
यस सर, यस।
और प्लैटिनम आपने इसलिए सिलेक्ट किया है क्योंकि हाइड्रोजन की डिफ्यूजन प्लैटिनम के अंदर बहुत तेज होती है। इंस्टेड ऑफ नाइट्रोजन एंड ऑक्सीजन, हाइड्रोजन तेजी से डिफ्यूज होता जाएगा। Alright?
Alright, sir.
So this is one of the example. Okay, so we'll stop over here. We'll look at one of the